All right, Deborah, we have our next speaker coming up. We have Robert Mao, and he's going to be talking about migration to Azure Blob Storage and Cosmos DB from Couchbase / Elasticsearch.
Hey everyone, 1 second. Awesome. So, hi everyone. My name is Robert Mao. I'm a software engineer on the monitoring infrastructure team here on LinkedIn. And today I'll be talking about NoSQL Cloud Adventures, our journey in moving our product from Couchbase and Elasticsearch to Azure Blob Storage and Cosmos DB. It's an honor and a pleasure to be with you here all today. So, to go through this, what we're going to talk about first, we're going to talk about what our product exactly is. In this case, Inmod. The background on the Couchbase and Elasticsearch setup that we had for it, how we set up Cosmos DB and Blob Storage to replace these two things, and finally, the juicy bits of the topic. What are the takeaways that we feel were most important from this entire journey? So, starting off with Inmod. Well, what is Inmod? In a nutshell, the purpose of Inmod is to generate synthetic requests and to visualize test results for real-time availability monitoring. This is an internal tool that we developed over here. Language-wise, it's written primarily in Python for the backend, a bit of Golang, and primarily with vanilla jQuery for the UI and other bits. In terms of what it's equivalent to on the open market, it's roughly about there with Catchpoint and Uptime Robot, if you're familiar with those tools. Tools essentially for synthetic monitoring and getting a live view of how your test runs. And here at LinkedIn, it's used by dozens of teams here for internal tooling and external endpoints that you might be familiar with, such as sales, recruiting, payments, all kinds of different bits and functionality of the entire site. And if you look at the two screenshots that I have over here, I mean, what generating synthetic requests means in practice is you take a URL and then you poke it over and over. And if anything goes wrong with this URL, well, then you'll see that immediately with a test result, and then you could dive in and troubleshoot. If you look at the top page, the top screenshot I put over there, you can customize a list of tests, a list of endpoints you put on a home page. Back before COVID, when we were still in the office, it was not an uncommon sight to see teams set up a custom list of about a dozen or so tests, as you can see over there, put that on the TV screen, and just have it there, like in a workspace area. If those green boxes start turning red, or if they start disappearing entirely, then you notice something is up with Inmon, with the site, or with your product, and you should probably take a look at that immediately. Likewise, you could dive down into the plot page below and take a look at the health of your service over time in the immediate last 5 minutes, hour or so, and just get like a brief overview into how your service is doing with the synthetic pokes from Inmon. As far as what kind of tests we support, again, we poke a URL over and over, and there are two primary ways we do this. You can crew an endpoint and get back the result, or you can run a full-blown Selenium test on the endpoint, loading up in a browser, running JavaScript, all that kind of stuff. And as far as how you determine whether the result was successful or not, there are a bunch of ways you can validate it. Some of the most common ways we do are status codes, 200s, 4xx's, and everything, running searches and checks over the response body and content, all that sort of thing. And you can see an example of a test result to the right. So, one other thing that we do on top of running these test results is we save what are called call trees. In the open world, these are better known as distributed tracing. The idea is that when you run, when you hit a given URL, it's going to touch a lot of stuff behind the scenes. We manage this via Kafka here on LinkedIn, and we generate all these service call events when you hit a URL. So when you hit a URL and it fans out and touches other stuff downstream, all this will be saved via Kafka, and Inmon will collect these results and return them back to you via the UI. These call trees can be quite small, as you can see on top, quite bigger, medium size, as you can see at the bottom, and really big, too big to fit on one or even two slides over here. And the idea behind these service call trees, these distributed tracing events, is if a given test runs, fails, you could then drill down to what service may have responded with a bad error code, what service may have taken a long time, and then easier troubleshoot what may be wrong with your test and service that you're testing. Now, architecture-wise, to give a brief overview of how Inmon works, we have Inmon Web, which is the UI portion whose screenshots I showed earlier. That's what the end user will primarily interact with to view results, create their tests. Inmod Web will talk to our configuration data store, previously Couchbase and Elasticsearch, now Cosmos DB and Blob Storage. The configuration data store in turn talks to the Inmod scheduler, which fetches configs on intervals and sends them off to Inmod tester, which does the job of curling or running a Selenium test on the URL in question. Inmod tester will then send off its metrics for monitoring and visualization of these test results over time, and Inmod tester in turn will send its results over to our result data store. We have a separate app, Inmod extractor, that will talk to Kafka and scrape all these service call events from the various Kafka topics, and then shove them back into the result data store, where then Inmod Web retrieves both results and call trees for you to go ahead and view at your leisure. So to give you an idea of like what kind of scale we run at, we have approximately 40 million test result objects with associated static object blobs, things like screenshots, response headers, response bodies, and such, sitting in Cosmos DB at this time. These 40 million results are the result of about 1,700 active tests, running at minimum once per minute, but more often once every 15, 20, 30 seconds. Again, this is Inmod is meant for live monitoring of your service. And as far as call tree objects, we have about 120 million of them currently stored within Cosmos DB. This 120 million objects was in Cosmos DB post-migration came from 1.5 billion call tree documents in Couchbase prior to the migration. So we definitely were able to see significant storage improvements when we made our migration from Couchbase and Elasticsearch over to Cosmos DB. So with that in mind, let's talk about how exactly we ran Couchbase and Elasticsearch. So there are 4 primary objects that we store within our data store. The first is going to be static objects. These are things like screenshots, test response headers, and so forth, binary blobs, that kind of thing. We have call trees, again, the distributed tracing, where for a given call tree associated with a test result, there might be anywhere from 10 to 100 or even more than 100 individual service call events, all stored as JSON objects. There is a test result object itself, which is a JSON object containing the test result run info, status code, what host service did, that kind of thing. And lastly, we had the test configs, which are the JSON definition of the test itself. What URL you're hitting, what status codes you're looking for, the validation criteria, that sort of thing. So with that in mind, what were the challenges we faced with Couchbase and Elasticsearch? Well, to start with, why did we pick Elasticsearch to run in tandem with Couchbase? This was because of problems that we saw with Couchbase's index slowness. At the time, Nickel, its query language, wasn't quite stable enough for us, so we elected to run Elasticsearch on top of Couchbase to query through and grab our data on the fly. Now, the problems that we saw with Couchbase were that it ran out of memory very frequently, and we got pinged on call for this a lot as our tests grew and as we ran out of memory. We suspect that the internal retention for Couchbase objects stopped working due to bugs with it, and the end result for this was that screenshots and logs were dropped from our saved test results. And this presented a real problem because users would come to us occasionally asking, hey, my test failed for whatever reason, but I can't look at the screenshots and I can't look at our response headers and bodies to see what exactly went wrong. So this led to blind spots in our monitoring. To try and get around this, we bumped the memory quota on the separate bucket that we use for static objects as a stopgap, but this will only work for a couple of days or weeks before it fell over again, and we had to go back and do this over again. On top of that, our call tree bucket cross-data site replication would get wedged, leading to even more out of memories. And ultimately, this caused us to pause across the data center replication entirely from a region, leading to a single region being our only data store fabric for this app and putting us in a rather vulnerable position. So with that in mind, we needed to go and find another solution. So why, though, Blob Storage and Cosmos DB in particular? Well, to this end, we explored a number of different options. The first of which was Espresso, which is an internal document store that we use here on LinkedIn. We considered it, but Espresso was expressly designed for balanced reads and writes, and our traffic is much more write-heavy than read-heavy. The vast majority of the test results that we shoved in are successes, which people are not typically interested in, They're more interested in failures, which constitute perhaps 1-2%, if everything's going right, of the overall test result set. So that was also not a win. Plus, Inmod monitors Espresso, and using something that we monitor directly within the tooling that we need to make it work didn't seem like a particularly wise idea. Here on LinkedIn, we also run CAS, Couchbase as a service, which another team manages, but they explicitly said that this service is meant to be used as a cache to speed things up, not as a source of truth, which was not accepted for our use case. We needed a solid, bulletproof data store for what we were doing. We also thought about just obtaining additional Couchbase and Elasticsearch nodes, but this wouldn't really have addressed the internal retention problems that we were facing. It would have cost us quite a bit of money, and this would have been undone with Blueshift, our ongoing internal migration of LinkedIn apps over to Microsoft Azure. Lastly, we looked at Kusto and Inlogs, which is another solution here at LinkedIn for storing logs, various objects, but this would have required a major refactor from our consumers and how they query data from Inmod's API. So that was also a no-go. So after exploring all that, we hit upon Blob Storage and Cosmos DB, which checked off all the 3 boxes that we were looking for. It's available. Microsoft's very good about keeping these things up. It's scalable as much as your wallet will allow for however much data you're shoving in there, and it's stable. Microsoft, again, has a vested interest in keeping these things up and running as much as possible. So moving on to static objects and design considerations therein. Frankly speaking, using Couchbase for the binary blobs that we were storing within it was not really a good idea. Couchbase was not really meant for storing things like images or stuff like that. But it was a perfect fit for Azure Blob Storage, a key value store. One thing that we did have to keep in mind was the number of write operations. Because Blob Storage bills you by the number of individual writes, it made sense to go and we write way more than we read. What we did was, for our key, we took the test result ID, and for our value, we took we now stored a gzip archive containing all 5 or so static objects, screenshot, response header, response body, and so forth into one. Previously, with Couchbase, we would store each of these things individually, but with Blob Storage, we chose to store all of them at once, merging 5 or so writes into one to save on cost for us. And when reading, like when you click on the button for screenshot, when you click on the button for response header, behind the scenes, the UI will then pull the entire gzip archive. It will then unzip on the fly and dump the individual object we're looking for. Again, because we write way more than we read, and the reads are limited largely by user traffic, because the users clicking through the UI, we felt that this trade-off was very much worth it for us to save on the cost of individual writes to Blob Storage. And architecture-wise, this required changes only to 2 of our apps, Inmod Tester, which runs the tests and shoves them back in Inmod Web, and Inmod Web, which takes the tests that Inmod Web, the objects that Inmod Tester gives over, and shoves them now into Blob Storage rather than Couchbase. So moving on, you can get an idea of the kind of scale that we run at. As you can see, as mentioned earlier, we write way more than we read. As you can see, like something like, almost like, yeah, an order of magnitude, like more than, we write pretty much an order of magnitude more than we read. And you can see that the performance-wise, the vast majority of our queries and of writes and reads performed quite admirably, with most of them running in under 500 milliseconds, with very, very few, almost none, none over here, running over 5 seconds. So pretty bulletproof service in our experience. Yeah, and over here you could see, again, way more writes than reads. So yeah, perfect. Again, in our use case, it made sense to go and bundle together those writes, and even if the reads ended up being a little more costly. But yeah. Moving on now to call trees, what we call distributed tracing. This was the first use of Cosmos DB for Inmod, and it was a very successful one. As soon as we set this up, the constant on-call incidents at the rate of 3 or 4 a week that we got for Couchbase and Elasticsearch essentially went away, even though we were still using those for test results and test configs. We only had to change 2 of our apps, Inmod Extractor and another one called Inmod Retention override, Extractor check is the app that checks Kafka for the service called event nodes, and now sends them off to Cosmos DB rather than Couchbase. And retention is something that we have for just going through and updating like the time to live per node for results that users may want to keep longer in our data store for further examination. We also changed the Inmod web for reads to hit Cosmos DB rather than Couchbase, and we made other changes for partial call tree node storage, indexing, and collecting as many call trees nodes in memory in one go for to minimize writes, in keeping with the theme of minimizing individual writes over to Azure services to save on cost. Here's an example of an individual call tree object that we store. As you can see, just an object, and it contains stuff like caller container, environment, hostname, and such, what particular hostname service it, what URL it's hitting, and then its fan out. Like when it hits something, what do its children hit, and what do their children hit, and so forth. So you can really make quite a massive tree from all this stuff. And again, getting into some of the numbers and metrics, as you can see, Cosmos DB is pretty much as bulletproof as Blob Storage over here. We're on the order of like 60, 70,000 writes per minute, and very, very few errors, just a few flukes now and then. And lastly, moving on to test results and configs. So for test results, again, we only have to make changes to Inmod web. For Inmod tester, we can retain the same path for result emission. What did make things a little bit more hairy for results, though, were query-based indexing. We learned particularly over here that partition key selection is very important. Cross-partition queries are pretty slow, and you really want to make sure as much as possible that when you query something, it sticks within one partition. So with that in mind, for test results, our partition key ended up being test name, since the vast majority of our queries are going to be for a given test or a given set of tests, and test configs. So this test configs weren't as important because we store way fewer of those than test results, but it made sense just for cleanliness to store config type, the actual live tests, the test revisions, and so forth. And on top of, to try and get around the problem of working around cross-partition query updates, we would only set up composite indexes on fields on which we actively search. So on top of the test names, we will also search on stuff like successes, failures, so we can go ahead and grab, okay, a list of tests that were successful, a list of tests that were not successful within the past half an hour or so. And again, moving on to metrics, the request latency that we saw for Cosmos DB in this regard was also pretty excellent overall. Again, vast majority of requests on the order of 500 milliseconds or less. So, takeaways from all this. So for static objects, test results, and call trees, our migration went pretty smooth. And the reason for this was because we store test result objects for a maximum of 30 days. And the idea behind anything after that, it just ages out, we delete it to avoid holding onto it forever and raising our storage costs. So for this reason, we were able to get away with a dual write and read strategy to make our transition from Couchbase to Azure very seamless. What we did was, once we got our Azure installation up and running, we started writing and reading to both Couchbase and Azure for 30 days. After those 30 days were up, we had the same set of data overall within both Couchbase and Azure. We then turned off reads to Couchbase, but kept writes on, just in case something went wrong, and we would have to fall back. After we were confident, about a week, 2 weeks or so, that Azure was serving everything, nobody was complaining that they couldn't find the results and such, we then turned off writes to Couchbase entirely and then decommissioned our Couchbase cluster, moving on to Azure entirely. Test configs, though, because those aren't aged out, unlike test results and stuff like that, we did have to go and manually migrate those from Couchbase to Cosmos DB. But because it was only a few thousand JSON objects, it was not a particularly difficult job to write a one-off script to download our test config objects and then shove them into Cosmos DB and to have them up and running. Now, if you're moving a substantially larger data set, if you don't have the luxury of just having stuff age out and be able to read and write, we did some looking around and found that Microsoft for Cosmos DB does offer inbuilt tools for stuff like MongoDB to go and migrate existing data over to Cosmos DB. So worth keeping in mind. Other stuff that came up were, so we use Python for this for our app, and so the Python Cosmos DB client, there were some API changes mid-development that we had to deal with. Sometimes this helped. For example, we got official support for an external proxy that we use to go and talk to the Cosmos DB API rather than have to wire it in ourselves. But other times it caused issues. For example, we found that the retry logic in the API client didn't really work, and we had to improvise and implement this logic ourselves. There was some other stuff that we had to keep in mind, like translating some Couchbase functionality within Cosmos DB. Counters and atomic updates required using Cosmos DB's optimistic concurrency control via the ETAC headers to ensure that writes didn't get lost. And this functionality mapped over very neatly from Couchbase or to Cosmos DB. And again, to re-stress this point, partition keys, partition keys, partition keys. This part was very crucial that we found when we were setting this up, because when you pick a partition key, you can't change it. You're stuck with it for the data set, and so that first choice is very crucial. You got to emphasize, like, to avoid cross-partition queries whenever possible. It can be done, but if you're going through many partitions, some of these queries can be on the order of like 30 to 40 seconds. And if you're doing an offline processing or just tweaking around behind the scenes, this is a big deal. But if you're trying to do things like pull test results by response code or something else, like across all different test names, where we don't explicitly index or partition on, then these things can be quite slow. We suspected that the Python Cosmos DB client didn't do parallel queries. Like if you were running a query that's, for example, spanned 100, 200 or so different partitions, we suspected, but we aren't quite sure, that it would go through them iteratively rather than in parallel, which is quite slow. However, we found that as of December 2021, last year, there is now an asynchronous client for Python for Cosmos DB where you can fan out and make these queries in parallel. So yeah, I hope you found out that useful. It was definitely quite a journey migrating from Couchbase and Elasticsearch over to Cosmos DB and Blob Storage. And I'm happy to take questions now. Thank you very much.
Hey, Robert, great, super amazing session. I really love to see all the great improvements that you guys made. I wrote down a couple notes, like I saw you had 120 million call tree objects in Cosmos DB versus the 1.5 billion in Couchbase, which is really notable on my end. I was just curious about your partitioning strategy, by the way. You mentioned the PK for the test results was just test name. What was the PK for the test configuration?
A test configuration, yes, I should have mentioned that, stressed that more. A test configuration was just a test configuration type. So for a given, like a test, like we'll say like foo, bar, whatever, you will have like the live test right now. So that would be for test config. We'll just call that like test config, and then we'll also have revisions. So past like versions of the test config. And then if you're looking for revisions, you could just draw for that. So we partition on config type.
Oh, got it. Cool. This is really, really great to see.
Well, I think you distilled kind of the essence of partitioning super well. I wrote a note to ask, what was your partition key? And then you had a really great section on it. I think the advice you give is spot on, especially I imagine at the scale you're running into. If you have small app, cross-partition queries is typically fine, no problem. But once you get to, I think, the millions and billions of records that you're storing, I definitely want to get those single partition queries.
Absolutely.
I also wanted to call out one other thing that I thought the kind of journey you shared was really exemplified really well, which is that there's a limit to how much you can scale up by just adding more CPU, memory, and storage. And at some point, these kinds of traditional systems have a natural bottleneck. And to some extent, it sounds like you were actually just scaling up memory for quite a bit of time. You get on call, add more memory, on call, add more memory, until finally you decide to make a shift. Can you tell us a bit more about kind of how you and when you finally decided to switch over?
Yeah, so like I mentioned during the talk, using Couchbase and Elasticsearch for stuff like static objects was frankly kind of an ill fit from the very start. So we were running into problems for that, but it was like a stopgap solution that we made. It predated my time here at the company, but it came to the point where just after a few months, where we started just getting constant pings, like for the alerts that we set up, like on the order of like 3 or 4 a week, then we really just started putting our foot down and saying, all right, this isn't going to work. It was when these incidents started rolling in that we figured that this isn't going to work. We should start looking at something else. And that's when we went through the internal process here to go and like request Azure Cosmos DB, Blob Storage subscriptions, and start actively looking into that to decom Couchbase and Elasticsearch entirely and move over to that.
Cool. I also had another follow-up. So you have like a very high write-heavy workload. I think you said something like 50 or 70,000 writes per second, something like that. And during that migration process, you mentioned something about having a shift between the writes having 5 writes in one, or compressing all of the writes. Can you go into like some more detail about what that was?
Yeah. So that was for blob storage.
And
when we worked with Couchbase and had all these different things, so the static objects will be about 5 or so different objects. We have like console logs, response headers, response bodies, screenshots, something else, hard files, some other things I'm undoubtedly forgetting right now. Back when we ran on Couchbase, we would shove all these things individually into our data store. So we would store, like, for example, result ID, result ID screenshot, result ID response header. Now, we found that blob storage will bill you for the amount of individual writes that you do. So it made a lot more sense for us that when we generated a test result object, we would save these 7 or so disparate objects into one gzip archive, and then shove the entire archive at once into blob storage, rather than shoving the 7 in and pulling the 7 individually out. And this saved us a bit of cost as far as running blob storage goes.
Cool. That seems like a great improvement.
Yeah, and in a similar vein, we did the same thing for call trees. Again, like a single call tree might have like upwards of like 100 different nodes. So as we scraped Kafka, we tried to cache as many of the associated call tree nodes together in memory, and then shove them in. We might not always get like one perfect write for every individual call tree. It might be 3 or 4 or 5 or 6, but 3, 4, 5, 6 beats 100 individual writes by far.
Definitely. I've got one last question for you. Is you mentioned your teams are one of the first teams within your company, LinkedIn, to actually start using Cosmos DB. Do you have any advice for newcomers to Cosmos DB on how to learn the service and start their apps, or maybe even considering a migration themselves?
Anyways, yeah, definitely read over the documentation thoroughly. If I had, the partition key stuff was something in hindsight that, just looking through like use cases, looking through documentation would have been big. And one other thing that I would recommend is set up like a dev subscription. And the emulators are nice, but there's nothing that beats the actual thing, the live thing, for just playing around with it. When I was developing for all the stuff, I had my own an exact dev setup for test configs, results, call trees, and static objects. I used to just play with everything. So play with everything locally, very thoroughly before you shove it into prod.
Oh, that's good advice. Thank you so much, Robert.
My pleasure.
Thank you so much, Robert. Really great session.